Hello and good day to you. So today I'm doing fixed and random effects in hypothesis testing. I know it's a little bit jarring from what we were doing on linear regression, but I felt that I wanted to get this out of the way because I feel that it improves your model, and it gives you a way of understanding a load of things that are happening, and what to remove out of your model to get rid of stuff. And I think that's pretty powerful because, as you sort of saw probably last time, you might have used the car key information coefficient. You might have helped you pick out particular variables that were part of your linear regression. But you probably noticed that if you've got a big set of data, you don't know what you're really putting in, and the more variables you stick into a model, the more likely it's going to overfit. So, like the saying goes about programmers in general, bad programmers write code, good programmers delete code, and I think that goes for good data analysts delete variables from linear regressions. So anyway, we're using the data from the life expectancy from Kaggle. So if you want to follow along, please do. Using the libraries LME4, LMER test, LS means, and LME. Oh no, sorry, the last one. Don't put that in. That's slightly different. I need to delete that from my script. Oops. So this is about designing tests. This is about trying to get as close to working out whether you know a given variable should be in your data. And I know we talked about ANOVA test, but I feel like this pushes the boat out a little bit more and gives you something to talk about because it focuses on variance. And hopefully now, having gone through learning a little bit about linear regression and seeing about the residuals and talking about variances, I think you might get this a little bit better than if I'd have gone into it straight away. For obvious reasons, like everything in R, you need to use the na.emit on your data. If you're doing this properly in the real world, you should actually go and check your NAs and ask the question, why are they NAs? But let's not go into that. What you'll be using is the LMER function, which works like this. And what you'll be putting in is your first value, and this looks like a lot like a linear regression if you haven't noticed, and the LM lot like a linear regression. So we're trying to work out, is there a relationship between the status, developed to developing, and the life expectancy of this within the data. We've blocked out country as a fixed value, and we've done year as a fixed value. Now, if I'm to do a summary, what you'll get the variance, and you can. And what I do like about this as a process is, if you put it in as a random effect, you will get an idea of how much variance is coming out of that item. And if you've got the fixed effect, which is usually the one you're more interested in, you've got the same again. And as you can see here, while this just did a random effect and did data country and gave the variance for amongst different countries, fixed effects will break down the estimate and standard area and do a hypothesis test for each of these. So as you can see, it's a good way of limiting down to your specified variable that you're trying to test and try and work out if it has an impact. The best explanation I've had for what you're using this for is if you were had a bunch of salespeople and you wanted to work out what strategy is important and what gets the most payments. What you'd need to do is block out things like you couldn't have an instance where the client and the salesman were left as a value that you were testing. So you'd need to make it a random value. And as you can sort of see, if you put one line or, it's the or sign in C++, and then your variable, that's what makes it a random variable. And when you're designing tests, the sort of advice I've had is things like time. Does time affect the experiment? If yes, it's going to be fixed. And if no, fixed with and random, so do both. If linearity of time is assumed, add the numeric, and if not, add as a factor. I.e., if you know that you just naturally, your salesman naturally was selling more each year, you might just put in the year. But if different years had different impacts and it looks like an up and down, you might have to put it in as a factor. And the great thing about doing it like this is, say you've got, and I'm using time here as a representative to make you think about it. You can add time in, see if it's significant, and then drop. So if we look here, date year, there's only a variance of 2.7. So that's probably not worth keeping in our model, and you wouldn't end up leaving that in when you got to doing your linear regression. So hopefully we've blocked out the right things. And the reason, going back, the reason why you do both random and fixed, if time, for say, affects your model, you want to get as very close to the mean as possible, and doing both increases that. So what we can then do, we can do an ANOVA, if I spell it right, and then your ANOVAs are obviously going to be much more accurate because you've been able to block out these other variables and set them as fixed. And actually, if you were doing this and trying to come up with a linear regression, seeing the amount of variance in country and developed versus non-developed, that might make you include both. But you might see that you get such a good model with just one that you only need to know that one thing, given the specific subject matter of mortality. Maybe that was the wrong thing to point out. But then moving forward, you can use this result LM function. The result LM is the variable I'm using to assign it to. The LS means is the function from the LS means package. You're handing it over the E variable which we've stored our test in, doing a pairwise and status, and this then lets you sort of split it up, and there you've got your top breakdown of the mean, lower and upper. So you could sort of sit here and say, actually, after doing all that, after having removed these other effects of country, we're able to sort of turn it into a confidence interval, which is really what we want to get to. Because imagine if this was salespeople, we would have here the list of names, and we'd have the lower outcome, and it's in the 95 percentile as you can, confidence level, as you can see here, and the upper confidence level. And as you can see here, that's a variance of 7, and in the developing world it's a variance of 3. So if you were using this to work out whether a given variable is important enough to chuck into your linear regression because you're having some confusion over it, this is really useful. And I also think it's really useful because I can see a bunch of, it's the first time I came across a test where I sat there thinking this has real value to managers because that you can use it directly on performance, directly on describing somebody's behavior by doing it this way, because having blocked off your other variables and having assessed the variance related to them, you can put that down on a PowerPoint page in the appendix, and you can put this this confidence interval up front, and you can say, we think this is the behavior of all these these other people. Here's the list of other variables and how much variance they contribute. If you would like me to do further work on them, do let me know. And I think that's very powerful, and there's part of me that wished I'd sort of sat there and done all the hypothesis tests just one after the other, but I do feel that I get it better now having gone on to the linear regression, and I hope you feel the same way. Thanks, have a good day, bye.